That was 17. Okay, 18 and 19. '18 says, '18's about average product, and what do I do? Capital? Okay, and then 19 does marginal. Okay, so 18 says, I've got this linear production function. Quantity is equal to 3K plus 4L. And then I made it too easy by saying, what is it when I've got L is equal to 10 and K is equal to 10? Okay, so average means total divided by whichever particular input. Right? So in this case, if I plug in 10 and 10, I get the total output is 70. And then I asked for capital. So in this case, I'm going to divide that it took 10 units of capital, which means like 10 machine hours. And so the answer here is 7. Now, by making those equal, nobody had to think about what to divide it by. So I made that too easy. The other thing is normally, the other common mistake people do is they forget to divide it by the input. So they would give me the answer 70. So normally 70 would be answer D, and then 45 would be answer E. Okay? Good. 19 says, we're doing marginal. So right now I've got this linear function that's, again, quantity is 5.2K plus 3.8 L. And I asked, when K is 16 and L is 12, and I asked for what's the marginal product of capital. Okay, so you're going to be thinking, hey, marginal, that means I'm probably going to be taking the derivative of something. Okay, so if I'm taking marginal product of capital, I'm taking the derivative with respect to K. So it's going to be 5.2. So that's the answer there. Does it matter that I gave you K is 16 and L is 12 there? No, not with a straight line like that, it doesn't. Okay, not with a straight line. Where it's going to matter is in just a second when we do with a curve. Okay, but with a straight line, that means it doesn't matter that if I go from 999 to 1,000 or 100 to 101 or 5 to 6. If I add one more unit of capital, this is forecasting. This is saying you're going to get 5.2 more units of output. Okay, it's a straight line. Where it would matter, where I'll give you a second to work with your neighbor, is let's go to our example here of what if I did it with a Cobb-Douglas function where I've got square root of K times square root of L, right? I'm going to just fix capital right now at 1. Okay, and then I'll have you evaluate L at probably 9 and 16. But if this is my function, so I could rewrite that as 1 times square root of, or 1 times L to the positive 1/2. Okay. What is the derivative of this guy with respect to L?
1 over 2 squared root.
Okay, so what do I do with this 1/2? Bring it down, that's easy, right? I'm going to 1/2 times 1. Okay, now what happens to the L to the 1/2? Yeah, so I said just like if I had it be 4L cubed, and so that became 12L squared, where I did 3 minus 2. I'm going to make this times L to the negative 1/2. And anything raised to the negative? Yeah, so it will be 1 over L to the positive 1/2. Okay, so now that's our marginal as a formula. Okay, and so now I could ask you to, I could plug in, I could say, hey, what if evaluate it when L is 9 and L is 16. And all you would do is plug in 9 and 16 there. Okay, so if you plug in 9, that becomes 1/6. So that's my slope right here. And if I plug in 16, this becomes 1/8. And if I go all the way out here to like 25, then it becomes 1/10 and all the way down. Okay? So here, when it's not linear, it matters where I am on L. When it is linear, or linear here, I mean, I said, what if K is 16 and L is 12? Here it didn't matter. Those are just distractors. Okay? So with that, that's where I'm going to end this. So you're